Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and welcome to the third lecture of week 3. We will start right away. This lecture deals with spherical coordinate system, that is the third of the three coordinate systems that we have been discussing so far, and this is the last one and perhaps the most difficult one, a little bit difficult one to explain. But if you're able to understand this lecture, you will be, this coordinate system especially, you will be able to, I can guarantee inshallah, you will be able to understand one big portion of electromagnetic fields, that is electrostatics. Okay, so in a spherical coordinate system, as you might have guessed, that we have a point and we want to locate that point. In three-dimensional space, we have a point and we want to locate that point. And one additional knowledge is given to us, just like in the case of cylindrical coordinate system, that this time the point lies on the surface of a sphere. So, okay, surface of the sphere means that now we have to locate this point, which is located on the surface of the sphere. Now, we have to establish x, y, z axes, all right, so that we can study spherical coordinate system relative to the most general case, which was Cartesian coordinate system. This was the same thing that we did in cylindrical coordinate system as well. Although we had a point on cylinder, yet we established x, y and z so that we can define direction in cylindrical coordinate system. We can define coordinates in cylindrical coordinate system and try to relate that to the Cartesian coordinate system, which is more natural to us, because we human beings can observe things which are wide, which has some height and depth and all. Okay, even if we see a cylinder or if we see a sphere, we also try to estimate unknowingly its the depth and height and width of a sphere and cylinders as well. So we human beings perceive things in Cartesian coordinate systems, all right. We try to observe everything in Cartesian coordinate system. It is a natural coordinate system to us, so it is always instrumental to study spherical coordinate system with respect to, or any other coordinate system with respect to the x, y, z Cartesian coordinate system, which we all are useful of. Okay, so where should we establish the origin of that x, y, z axis? The most intelligent way is to set these or establish the origin at the center of the sphere. All right, this might look like to you as a circle, but remember that this is a sphere. All right, so the point is on this sphere and we have set the origin x, where the values of x and y and z all 0 are at the center of the sphere. Why we did that? So that we can take the radius of the sphere as one of the coordinates. All right, remember that what are the coordinates? Coordinates are nothing but the address to that point, and if we want to find that point easily in case of spherical coordinate system, the most intelligent ideal way is to take the radius of the sphere as one of the coordinates. All right, so that our life will be a little bit simple. Okay, so one could have chosen center at here, but in that case, defining that sphere, this sphere, with respect to that center would be insanely difficult. So now what I can say that to reach from this point to that point, at least you reach the surface. That's it. Why I am able to say that? Because I am able to all right, sorry, let me finish. What I can say if I'm at the origin, I can say to reach that surface, to reach that point, at least reach that surface. That's it. Okay, no matter in what direction you move, first reach at the surface, then we'll talk about other coordinates. Okay, so if we have taken the center here at the center of the sphere, if we have taken origin at the center of the sphere, this allows us to reach the surface of the sphere in any direction. If in any direction I move the length of radius of the sphere, I will reach the surface. So one issue has been solved. So that's the reason why we took the origin at the center of the sphere. Why? Because radius of the sphere or the surface of the sphere can be reached from origin in moving by moving in any direction. How much? Radius of the sphere. All right, so it is always difficult to study spherical coordinate system in all the octants. If we consider the negative side of the y plane and y equals constant plane, and negative side of x equals constant plane, so it's always difficult. So we always try to we always establish the spherical coordinate system in the first octant and study that, and then we generalize it. So this is a sphere which looks like a circle, not very helpful. So if I just try to take one one octant, 1/8 of 1/8 of the total sphere, which will lie in the first octant. The first octant is the portion of the three-dimensional space where the values of x, y, and z are positive. Just like in 2 dimensions, we have got first quadrant, second quadrant, third quadrant, and fourth quadrant. All right. So first quadrant x, y positive, second quadrant x negative, y positive, third quadrant both negatives, fourth quadrant x positive, y negative. 2-dimensional space can be divided equally in 4 quadrants. However, 3-dimensional space cannot be divided into 4 quadrants. It can be divided into 8 octants. All right. So 8 बराबर हिस्सों में इसको आप divide कर लें, where the center with respect to the center. Okay, so if we take that 1/8 portion of the sphere which has x, y, and z all positive, that will be the first octant. So all right, so I would ask you to convert this all 3-dimensional diagram into or to take first octant of this whole picture. I need you to ask one thing. If I cut a tennis ball by a plane, what will I get at the intersection? What we will get is a circle. कभी अगर आप tennis ball को बीच में से काटें, the tool which you might have used must be a plane to cut it. All right. So wherever that plane would intersect that tennis ball, what you'll see a circle. All right. So let's say I've inserted a huge plane, which plane is actually xz plane, and or y equals to 0 plane here, and I have also inserted these x equals to 0 plane here. So this is the x equals to 0 plane, and I have inserted, this is the tennis ball, a very soft tennis ball, and I have inserted y equals constant plane here. So y equals constant, at the intersection of y equals constant plane and this tennis ball, what I'll get a circle. Something like this. Not very accurate. All right. So, but we'll get something like this. Okay. Maybe this might look like a little accurate to you. This was the point. Okay. So we are not interested in the picture which is below the z equals 0 plane, we are interested in only in the one which is, so we are also not interested in this because this line lies on the back side of the x equals 0 plane. Okay, and if I cut this remaining tennis ball by a plane which is x equals 0 plane, or in other words yz plane, what I will get? Again, I'll get an intersection which may be looking like this. Okay, and since I'm not interested in the sphere which is beyond, you know, y equals 0 plane, which is on the left hand side of the y equals 0 plane, I'm not interested in that. So at the intersection of y equals 0 plane and this tennis ball, I'll get this circle. Okay, although I'll get the other portion as well, but I'm not interested in that, so I'm not drawing that. And at the intersection of the tennis ball and x equals to 0 plane, which is nothing but yz plane, what I'll get? I'll get a circle. Obviously that circle will be complete, but I am interested in that portion in which values of x, y and z are positive. Similarly, if I would cut that cylinder sphere by z equals 0 plane, which is nothing but xy plane, what I'll get? I'll get a circle, but I'm not interested in the rest of the part of the circle. I'm interested in this part. So now I would advise you to look somewhere else, you know, blink your eyes a little bit and come back here. Okay, so this is, you know, a spherical surface, 1/8 part of this, that tennis ball or the sphere on which that point P lies. Remember that the radius of this sphere is maybe r. Okay, so if you are at this point, now how to reach that point using the spherical coordinate system? We define a spherical coordinate system such that in cylindrical coordinate system we said that move in the direction of a reference axis, how many units? Rho units, or so many units that you reach the cylindrical surface. Now we would say from here, move in the direction of the reference axis, how many units? So many units that you reach the surface of this sphere. Okay, so now this time we take z axis as the reference axis. All right, this is the reference axis. Now you have reached here. Okay, now suppose this is the North Pole. You were living in the core of the earth and you now decided to move at the surface of the earth. So you move from the core, assuming that the surface is that the planet earth is a perfect sphere. So you must have moved from the core center of the earth. How many units? Radius of the earth units, RE units. All right, now once you have reached here, and let's say your target is here, you are here at the North Pole, and you can see that, okay, from here you can see that here is a huge flag, and you can see, okay, this is my point to where I should go. So you will now travel along that surface, along the surface of the sphere, and you will reach your destination. Okay, so you will reach your destination. Now since you have moved along the surface, the distance between this point, which is our destination point P, and origin or the core of the earth will be RE, radius of the earth. But since we are defining a general coordinate system, we are not defining global positioning system, so we will say that this radius is nothing but r. So now let me just remove this flag. Okay, now you have reached here. Okay, so it means that you needed what? You needed the radius of the sphere, because this much units you moved in the direction of reference axis, and then keeping this constant, you moved towards your destination point here, and when you reached here, you realized that you are still at the same distance with respect to the center, and this line, which is now joining you at your final position and your starting position, this line is making certain angle theta with respect to the reference axis. Now this is now signifying that two coordinates are sufficient to reach a particular point in spherical coordinate system. Okay, is that the case? No, it is not, because let's say you reach here and now you want to call your other friends from the core of the earth. What would you say? Would you say reach the surface and then make angle theta with respect to north pole or the reference axis? Then you will reach me. You will reach, I am the leader of the clan, and you will reach me. If you are the leader of the clan and you are giving two coordinates to your followers to reach you, you must be a very stupid clan leader. Okay, because if someone now there is no destination here. Earlier when you reached here, you saw a flag here and you just reached that point, but now after reaching, you remove the flag and someone else came here and you said that, okay, after reaching the surface, make an angle theta with respect to north pole or the reference axis. So someone might have moved in a different direction from here to here, and again now this line, someone might have moved. Okay, let me redraw it. Someone might have moved from here in this direction, and when you realize that now I am making an angle theta, I should have reached you, but that is not the case. Why? Because from here there are several lines which are making angle theta with respect to z axis. So it means that there must be some third coordinate which should define our relative position relative to xy axis. Okay, because relative to z axis we have already reached. We have already known that relative to z axis make angle theta relative to xy axis. So one way is to establish the system something like this: drop the perpendicular from this point on xy plane, and then drop a perpendicular on y axis, and then drop a perpendicular on x axis. This will be y, this will be x, and this will be z. But can we use these x, y, z as the third coordinate? No. Why? Because the technical point about a coordinate is that if you are moving in one coordinate in the direction of one coordinate, if you change one coordinate, the other two coordinates should not be changed. Okay, like in the case of x, y, z, if you move in the direction of x, y, z constant. If you move in the direction of y, x, z constant, and so on and so forth. Similarly, we have defined unit vectors in the case of cylindrical coordinate system. If you move in one direction in which radius of the cylinder increases, or in other words, in which your distance with respect to z-axis increases, the other two coordinates theta and phi, phi and z remains the same. So if we say, okay, the third coordinate cannot be z, because we have already decided the height of this point in terms of an angle with respect to z-axis. How about the azimuthal or the position with respect to the azimuthal plane or the horizontal plane, that is xy plane? Can we use y or x as the third coordinate? No, because if I increase x or decrease x, okay, I will definitely leave the spherical surface, okay, because if I move from this direction in the direction of x, I will leave the spherical surface, and similarly if I move in the direction of y, I will leave the spherical surface. Why? Because my distance with respect to origin will increase, and now I will be on a different sphere, but the original point is on this sphere which has got the radius r. Okay, so what can be the third coordinate? The third coordinate can be, or can we use both x and y in order to fix the location here, in order to I can give my friends or my followers the direction that when you reach the surface north pole, make an angle theta with respect to north pole, and also stay away y units with respect to x-axis, and stay away x unit with respect to y-axis. Can I say that? I can say that, but in that case, obviously, those xy coordinates will not, number one, will not be independent. Changing x or y will force me to leave the sphere, number one, and number two, we will have 4 coordinates to define a three-dimensional system, which is totally redundant. So why not, instead of thinking in terms of xy, use an angle which we are already aware of, that is the radial angle a phi, just as we defined in this cylindrical coordinate system. Why not use that? Okay, now this now completes the picture. I can ask my friends, my followers, then when you reach the surface of the sphere, move in the direction of make an angle theta with respect to north pole, and make an angle with respect to x-axis phi. Make the angle phi, and you will reach me. Now any sensible person who is standing here will reach this point immediately using these 3 coordinates. So now the next topic would be how to define the fundamental surfaces in spherical coordinate system. So we'll talk about that momentarily. Okay, so now as you might have guessed, we've got 3 coordinates. So we should have 3 fundamental surfaces: r equals constant, theta equals to constant, and phi equals to constant. And moreover, for each fundamental surface, we should have a primitive unit vector which will be perpendicular to their respective fundamental surfaces, and which will also point in the direction of increasing values of their respective coordinates. So let's talk about the fundamental surfaces and their primitive unit vectors. Okay, and one most important point about primitive unit vectors, that if you're moving in the direction of AR, A theta and A phi should be the values of theta and phi should not change, and if you're moving in the direction of A theta, the value of r and phi should not change, must not change, and if you're moving in the direction of A phi, the values of r and theta must not change. So let's talk about fundamental surfaces and primitive unit vectors. Alright, so as per previous practice, I have uh, given here 15 diagrams which will aid you in understanding the fundamental surfaces. First is R equals constant surface, and we all know that R is nothing but radius of the sphere, or the distance of the point which we wanted to reach, okay, with respect to origin. So R is that distance. R is nothing but the distance between the point of destination and origin. So the collection of all those points which are equidistant with respect to origin is nothing but a sphere. So this is R equals to constant surface, which is a finite sphere. And just to show you that this is not a circle, this is a sphere, you know, depth and all. So I have just added a circle here and a circle here. Now you can see that this circle is nothing but intersection of the R equals constant sphere and Z equals 0 plane or XY plane. And this circle, which seems like a vertical circle, there is no concept of vertical circle, but which seems like vertical circle, is nothing but intersection of this R equals constant sphere and Y equals constant, Y equals 0 plane, or in other words XZ plane. Okay, so the diagram which we discussed previously on the whiteboard had this line, this line, this line, and this line. Okay, not line, curves. This curve, and this curve, which is the first, which is nothing but the sphere in the first octant. So R equals constant is done. Theta equals constant, the second fundamental surface. Theta was what? Theta was the angle of the line which is joining destination from origin. All right, remember, destination from origin, line joining destination from origin. Angle of that line with respect to Z axis or the reference axis was theta. So we said that there are several lines which are making the same angle with respect to Z axis. For instance, if this line is on YZ plane and this line is also on YZ plane, then where this is minus y, so this angle is theta and this angle is also theta. Okay, and this, so there can be several infinite lines which will make a constant angle with respect to Z axis. For instance, in this figure number 4, we have seen I've drawn two other lines, and this line is on XZ plane. If you drop a perpendicular here, from here you will reach x-axis. All right, so I can say that from this point, if I drop a perpendicular, I will reach x-axis on the negative side, and from this point also, if I drop a perpendicular, I will reach x-axis, the positive x-axis. Okay, so this line is joining this point, this line is joining this point to origin. Okay, and this line is, let's say, on XZ plane. So this angle is also making, this line is also making an angle theta with respect to Z axis. Okay, and similarly this line which is on negative x and y and Z axis is also making the same angle, as long as the sum of all such lines which are making the same angle with respect to Z axis will form a cone. Okay, so theta equals to constant is nothing but an infinite cone, a cone which is going all the way to infinite values of Z. I hope you will be able to understand that. So we can say that theta equals to constant is nothing but collection of all those lines, not point, because point does not make an angle with respect to anything. Collection of all those lines which make constant angle with respect to z-axis, which is a reference axis in our case, in the case of a spherical coordinate system. And I have shown four different lines. The two lines here are on YZ plane. Okay, the angles mentioned here. I have also mentioned two other lines just to give you an idea, which are on XZ planes. Okay, so now this circle is actually just to show you that this is a cone. Otherwise it will be an infinite cone, so this circle will be somewhere at infinity. You won't be able to see that, but it is really important to measure the radius of this circle. So if I want to find the radius of this circle, I can take this radius or the radius on the left hand side, and I know that this radius of the circle from this point to origin, this length is, let's say this length is r. So this length, which is nothing but the radius of the circle, can be found because we know that this line is making an angle theta with respect to z-axis. So now we have got a qaimatu zaira musallas, all right, I mean right angle triangle. Okay, so this is the right angle triangle. This is the radius. And so the radius now, radius will be, from your basic trigonometry, r sine theta. Okay, because this is the angle, so this must be perpendicular and this must be the base. And let me just give you okay, this will be the base. Or I can equivalently try to find it with respect to this line, which was on XZ plane, and that would be the same because this line is also making this line is along XZ plane, while this line was on YZ plane. This line was on YZ plane, but this line is on XZ plane, but it is still making an angle theta with respect to z-axis. So now again, if I join this point and drop a perpendicular on the z-axis, I will get what I'll get, a qaimatu zahira zawiya musallas, that is right angle triangle. Okay, this. So if this is again r, and this is the base, and this is the same angle, so the radius of this circle will be r sine theta. Okay, I hope that's clear. All right, and phi equals to constant because we defined phi in the same way as we did before. So that would be a radial plane of infinite width, infinite height. But always remember, it starts from, it has got a hinge at z axis. It starts from z axis. ये एक ऐसा दरवाजा है जो कि z axis से start होता है और फिर आगे infinity तक जाता है. So now in figure number 7, what I am doing, we are doing the same thing that we did before. We are taking two fundamental surfaces at the same time and trying to plot them together to find their intersection. Okay, so you can see that the intersection of a sphere and a cone is a circle, which I have highlighted here as yellow circle. Okay, so if I just remove the fundamental planes and show you the intersection, you'll get this. And I have taken arbitrary values, r equals to 3, radius is 3, and angle is 30 with respect to z-axis. Okay, so if I'm talking about cone, it means I am talking about angle with respect to z-axis. Okay, so this is the circle. So if I would take another cone, theta is equals to 30, theta is equals to, let's say, 60, I'll get another cone, but that cone will be wider. Okay, and that cone will intersect this same sphere at some wider angle. Okay, so we'll have a wider yellow band or yellow circle. So we can have several such circles, just like we have, you know, latitude in case of Earth global positioning system. You know, the globe, you have the North Pole at the top, the South Pole here, and at the middle we have got the equator, and then we have got these lines. These lines are what? These lines are nothing but intersection of the surface of the Earth and these infinite cones. Okay, remember that all these surfaces and the surfaces we talked about, the fundamental surfaces we talked about earlier in cylindrical coordinate system or earlier in Cartesian coordinate system, all are imaginary surfaces. They are not made up of any material. Okay, so Earth is made up of a material, but it always serves to give as a good example to understand. That's why I'm giving you the example of Earth. Otherwise, all these fundamental surfaces are nothing but material-less fundamentals, material-less imaginary surfaces. All right. So if you try to see it from the top, अगर आप यहाँ पर z axis पे चढ़ जाएं किसी भी तरह, and if you try to look down on Earth, you will see concentric circles, and those concentric circles will lie on XY plane. Okay, obviously each circle will have a different height with respect to XY plane, but if you see it from the top, perfect two-dimensional picture will be circles, concentric circles. Okay, all right, I think that's all for this combination. Okay, now again, if I want to find the radius of this yellow band, so what I would need r and I would need theta. R sine theta is the radius, because this length is, although the cone is infinite, no doubt, but this length is r, which is the radius of the sphere, because this yellow line lies on the intersection, meaning this yellow band is simultaneously on both the cone and the sphere. So the radius is r and the angle is theta. So radius, radius of this yellow circle will always be r sine theta. Now let's take figure number 10, intersection of r equals to constant and this phi equals to constant radial plane. Okay, so this resembles like the longitude which we have in the globe. Okay, all right, so earlier we had the circles, now we have semicircles. Because why semicircle? Because of the limitation of this radial plane. This radial plane starts from this this z axis. It does not go on the other side. It starts from here and goes the other way. All right, so it always covers half of the three-dimensional plane, half of the three-dimensional space. All right, not a space, I should say, but it cannot go the other way. This is its basic definition. That's why it's called a radial plane. So Had it been defined in a different definition, like we had defined x equals constant, y equals constant, and z equals constant, in that case, you know, you can see that z equals 0 plane or xy plane, where it is intersecting this sphere, it is forming a perfect circle here, okay, or here, or when it is being intersected by an infinite y equals to constant or y equals to 0 surface, it is giving us a perfect circle, okay, because x equals to constant or y equals to constant or x equals to 0 or y equals to 0 goes the both way, in the positive side of the z-axis and also in the negative side of z-axis for y equals to 0 surface, for x equals to 0 surface. For x equals to 0 surface, meaning yz surface goes all the way towards positive infinity to from negative infinity, okay, so it's infinite. So we have got perfect circles, perfect circles, okay. But just that you don't get confused, let me repeat what I just said, because the circle which I talked about is not mentioned here, so never mind. Since you can see that z equals to 0, or let's take y equals to 0 plane, which is xz plane, is an infinite plane which is symmetric about z-axis, you know, it is all the way towards positive infinity values of x, towards all the way towards the negative values of x, so it's a whole plane, so we have got a circle. But there is a limitation with this radial plane, it starts from z-axis, so it cannot go on the other direction, so we'll have, you know, the semi circle kind of thing here. That's the reason why the range of theta, because along this line, because this is on phi equals constant plane and r equals to constant plane, along this line the values of r and phi should not change. The only values which should change is the angle with respect to z-axis, or in other words the values of theta should change. So if I am, let's say, on this point, this is the destination, let's say, and if I join this point to origin, so this is theta, and let's say if this is the destination, and if I join this point to origin, now this angle is theta, some other value, but this angle is theta. If the destination is here somewhere, and if I join this point to origin, so this angle z, from z all the way to this point, will give me theta, okay. So theta will change, theta will maybe 30 degrees, maybe 50 degrees, maybe more than 90, some 120 degrees or so. So these are the lines over which values of theta changes, r and phi remains the same. So this figure shows the intersection only of this intersection of r equals to constant and theta phi equals to constant, without showing the other things, without showing the fundamental surfaces. Now just to give you a picture, these lines you can see on the globe, okay. Although on the globe you have got the markings on different like here we have got 90 degrees here and 0 degrees at equator, okay, but in spherical coordinate system we have got 0 degree here and 90 degree at equator. So just to give you the picture, although the values are different, and exactly at the London we have got the x-axis, because 0 degree is there, and then all the way from x-axis towards y-axis, So I've just changed the, a little bit of the orientation, but it is the right-handed coordinate system from x-axis to y-axis. Curl your finger from right-hand fingers and thumb will show you the direction. So here 0, 15, 30, and so on, so forth. So always remember that the intersection of r equals to constant and phi equals to constant curves, which are these yellow curves, they are always perpendicular to the horizontal or z equals constant planes. And now the third one, cone, and this theta equals to constant and phi equals to constant. So we have got theta equals to constant cone and phi equals to constant. Okay, so this plane is making certain angle phi with respect to x-axis. So we have drawn another line here so that we can get the upper limit of the intersection, although there is no upper limit because phi is also going up to z equals to infinity, and theta is equals to constant, cone is also going up to infinity, but we have to be finite to show you the picture. Somewhere at infinity, if they are meeting, you will get this point. This horizontal line is on phi equals to constant surface, okay, and wherever this line is intersecting the cone, that point, connect that point to this origin and you will get what? You will get the intersection, and that intersection is making an angle theta with respect to z-axis. And if removing the fundamental surfaces, we have got this. And from inshallah next class we'll discuss if we combine all these three fundamental surfaces, what we will get, and from there we will define the unit vectors, fundamental primitive unit vector, inshallah. So that's it for today, and study hard, stay safe, and good luck to you all. I know this course is taking a lot of your time, and it should take a lot of your time, because you by now you should have watched the motivation video, and that motivation video should give you the right impetus and the right push to study this subject really hard and spend some time in it. All that is 2 credit, but it demands a lot. And I can understand that you are really very busy with this. You must be very busy. Okay, till the next lecture. Assalamu alaikum.